So in this lesson here, we have only two small objectives here. The first objective is we're going to examine SI units and understanding what they are, and then we're also going to look at engineering notation, which is essentially just scientific notation with a slight modification that we use in engineering. So SI units, which uh, basically were established in 1960, um, and there's like I think a Latin or French name for it, but I just think of it this is standard international units. And of course, this is so that we, if we say 1 gram of something anywhere in the world, we know what 1 gram is. So some of the uh, standard units that you might be familiar with, like are meters. If you've taken chemistry, there's moles. Temperature, you might think Celsius, but it's actually Kelvin. And mass is gram, or sometimes people say it's kilogram. But I actually think it's gram that is used for the standard international unit here. And so let's look at the standard international units we will use for this course. Now, we're just going to look at the units here right now. We'll talk about in the next lesson or two about what these things are. We're going to have something here that you might be familiar with, charge, and you're actually probably familiar with charge. Everyone has, gotten a static electric shock before, and basically what you're doing is you're building up a charge on either your body or whatever it is you're using to give someone a shock on, and then basically you're making contact with another conductor, and actually technically you're not making contact. Technically you're ionizing the air, and you actually get a small bolt of lightning, um, and I say bolt of lightning as a bolt of electricity between um, uh, you and the device that you're touching. And the standard unit for this is the coulomb, which we denote with C. Now we have to be careful with this that you don't think of this as temperature, and the easiest way to know it's not temperature is we don't have degree C here, it's just C for coulomb. We won't use coulomb too much in this course, but it is the foundation for everything dealing with electricity. And then we have the, um, that's the unit current in a circuit. And the unit for this is ampere, which we often just abbreviate as amp. And the letter we use for that is just a capital A to represent amp. And then there is something that we will have as voltage, which again, it's something you're at least all familiar with to some extent because we've all used batteries before and had like a 9-volt battery, or your car has a 12-volt battery. So we're all familiar at least with what the voltage is as far as we've seen it before. We just might not know where it comes from. And voltage, what's kind of funny is that, well, that's the name, and that's also the unit is volts, and we use that as a capital V for abbreviation. And then the other one that we're going to be using quite a bit here is power. And power, of course, is how much, I like to think of it as how much power is being delivered, but basically kind of the energy being delivering, how much, you know, um, electricity you're using, how much ability you have to do some work. So power, and this is actually going to have a unit of watts, which we'll talk about in more detail, and that's just a W. Now those are the things that we would quote measure in a circuit that we're going to be primarily interested in. Some of the other things though is we'll have electrical components, which you might be familiar with some of these, resistors, and they have something called a resistance, and that's measured in ohms. And the symbol for this, though, is the Greek letter, and I always do a pretty crappy job of drawing it by hand. It's the Greek letter capital omega, kind of looks like the horseshoe. And then we also have capacitors, and the units for this are farads, and that is a capital F. And that's actually, farads is named after Faraday, was a physicist who did a lot of investigation with this and with capacitors, and he might not have actually, quote, been looking at capacitors per se, but he was developing the physics that we use to understand how capacitors work. And then there's also inductors, and these have a unit of henries, and again, that's named after a person, and we use capital H for Henry. Now, the other objective here, so that's our first objective, is all of those just being kind of familiar with some of the units we'll be using. Obviously, when we start looking at these, we'll talk about them a little bit more in detail. The other thing in this lesson that we're looking at is we want to look at engineering notation. Now, as I said at the beginning of this lesson, this is very closely related to scientific notation, which it really is just scientific notation with one kind of extra thing that we have going on here. Basically, scientific notation, we probably understand why we'd use it. I'll just give a quick example. So for instance, capacitor might have a capacitance of 0.0000000012 farads. And of course, writing this down is 0.00, I mean, that's a pain to write that down every single time with all those things. There's a couple reasons. One, it takes a long time to write, but then also you can't lose the decimal point, and then getting a real sense of, what this is, it's going to be dealing with a small number. And then the other thing is we might at the same time be dealing with something that is, for instance, a resistor that is 330,000 ohms. So we might be dealing with these kinds of things here and computations, and so instead of having to always write out these large numbers, we use scientific notation to, of course, make them a little bit more compact. So if we just went to scientific notation, we should all be familiar with this. We'd kind of move this decimal point over, and I'm just kind of showing, and you move it over to that spot, and so you have 1, 2, 3, 4, 5, 6, 7, 8. So this would be the same thing as 1.2 times 10 to the negative 8 farads. And then if we did scientific notation for this one here, we'd move the decimal point because the decimal point's right here, and we go back this direction. So 1, 2, 3, 4, 5, and so this would be equal to 3.3 times 10 to the 5th ohms. Now, that's all well and good too, and I mean, those are correct numbers as far as written with scientific notation, but in engineering we're like, well, that's even kind of a pain to always have to be writing times 10 to the negative 8 or something. So in engineering, what we said is like, okay, we're going to use prefixes to represent times 10, and I'll say to the n power, because it could be any n power. Now you're probably used to this because you've probably seen things, of course, like centimeters, which this is basically times 10 to the negative 2 meters. And so instead of writing times 2 to the negative 10, we just would write centimeters. Now, the thing with engineering notation is we always go engineering notation is always in powers of 3. So for example here, let me just make a small table. So it's not going to be necessary every single thing, but it's going to be the most common ones. And so I'll have the scientific, and then the prefix that we attach to the unit. I guess I didn't need that third branch there. So what we do is, I said, powers of 10. So I'm going to times 10 to the negative 15th, which honestly we don't use that one too much, but I'll still include it in our table. Whoops, I skipped negative 6 there. And we could go even further, but when we go to the positive exponents, we don't typically encounter something much bigger than times 10 to the 9th. And so the prefix here for times 10 to the negative 15th is something called femto. And actually this is, I'll use this column just to write the thing down here. So this is just a lowercase f. Times 10 to the negative 12th is pico. So this is just a p. Times 10 to the negative 9th is nano. So this would be an n. And then this is micro, which is the Greek letter mu. And then this is milli, or milli, which is a lowercase m. And then the base is just like the base unit. So there is no prefix, so that would be like meter, or in our case, like, farad, ohm, things of that nature. And then in this case, times 10 to the third would be kilo, which is lowercase k. Now this is the one we have to be a little bit careful with. Times 10 to the negative 6 is mega, which is a capital M, not to be obviously confused with the lowercase m. In text, that's obviously easy to pick up, but in handwriting, you need to be careful when you're doing handwritten things to make sure, whether you're referring to milli or mega, make sure that your capitals and lower cases are very distinct. And then times 10 to the 9th is giga. And that is a capital G. And now you could go further on like tera and stuff like that, but we don't typically have to use those. So to finish this video off, let's go back to these examples here. So let me first just, what I'm going to do is just lasso that, copy, put that away, copy and paste this down here so we can just look at this example again. So you'll notice here that with engineering notation, we always go in powers of 3. So if you're thinking about how you would convert this here, you would want to make sure that you do these in powers of 3 here. And what you want to do is you could rewrite these here. And so I'm going to erase some of this here. I'll go erase this little bit here. And so instead of going all the way up to 5, what we'd do here is we'd say, okay, we do a power of 3. And you always kind of want to do the power of 3 that's going to be the, quote, best suited. So I'm going to go only, that's 3 spots, and I'm going to go right there. And so this would be equivalent to 330 times 10 to the third ohms, which is the same thing if we use the engineering notation as 330 kiloohms. Now technically, I'm not going to show the work here, we could write this also as 0.33 megaohms. Now, We typically, especially with resistances, don't write them as like 0.33 mega ohms. We would write it as 330 kilo ohms. We typically don't do the 0.33 for that. It's not that this 0.33 mega ohms is wrong, it's just not the standard way we typically write it. Now, with this capacitor here, what we do is, okay, we're at -8, and if I look at this again here, if I had gone 1, 2, 3, that's still going to give me way too many zeros. Another power 4, 5, 6. Well, I could write it like that, but let's do 3 more. 1, 2, 3. So that's now 9. So this is the same thing as 12 times 10 to the -9 farads, which is the same thing as 12 nanofarads. And of course, you could also write this, again, I'm not going to show the work for this, but you should verify that this is also correct. You could write this as 0.012 microfarads. However, I'll box these here. These are the two that would be the what we would kind of say is the standard way of writing these here. And so what you need to become familiar with here is this table of components. We're going to be using these prefixes throughout the course. Now, you'll get used to them just as we use them. And then you'll also, when you're doing computations, of course, when you're entering this into your calculator, you would want to make sure to use the correct scientific notation when entering it into your calculator to do a computation. All right, so we're going to end the video here.